All right, this is going to be the kind of the introduction to experiment 26, resistances in series and in parallel. So I should be sharing the screen there. And now this has some CI uh, parts and some TI parts. We're mainly doing the TI parts, but I'll tell you when I want you to answer some CI questions. In fact, I think there's only one. I mean, some of them say TI, CI. If they say basically all the advanced study assignments, answer all the questions. Even this one that says CI, go ahead and answer that one. It really it isn't only a CI type question. So answer all the questions in the advanced study assignments. The At the intro here, if you read the overview, it says experiment 26 examines resistances in series, in parallel and series combinations with both TI and CI procedures. We're only doing TI procedures. We're not actually doing the physical measurements. We're going to do a virtual lab. So I've got the line crossed out in the CI procedure. Measurements are made with a voltage and current sensor, and graphs of V versus I are plotted. We're not going to do that. I'll probably have you'll need to do the plots yourself. And at the objectives, describe the changes in the slopes of V versus I graphs as more resistors are connected in series and parallel. We're not doing that portion of it. We're just going to stick with I'm going to make virtual graphs. I want you to read the theory. For series, resistance, that's this would be a series circuit. In a series circuit, there's only one current. Notice that you've got I here. That current goes through R1, R2, and R3. So there's only one current, but there's multiple voltage drops. So you're going to have a V1, a V2, and a V3. There you've got one current, but multiple voltage drops. The resistance, R equivalent for a series resistor, for a series set of resistors is R1 plus R2 plus R3, and so on, depending on how many resistors you have. And here it says the RS is the equivalent resistance of the resistors in series. Now, there's one thing to remember. RS, the equivalent resistance, will always be larger than the largest resistor in the bank. So if you have 100 and a 50 and a 25K, 100K or 50K and 25K, it's going to at least be greater than the 100K. It'll be 175K. You can add those up easily. Not so easy with parallel. And then here's a parallel circuit. Now in a parallel circuit, this voltage across here will be the same for all resistors, but you're going to have different currents. You're going to have I1, I2, and I3. It's too, well, maybe I can make it bigger. You're going to have I1. That doesn't look like an I. I1, I2, and I3. So you're going to have one voltage across here, but you're going to have three currents, okay? It's going to split up into three currents. They show it here splitting up, and like in a water pipe. Now let's get over here to the R equivalent. For RP is R equivalent. Notice that if you do this calculation, oops, if you do this calculation, you're not finished. You have to take the reciprocal of this 1 over RP. I express it, RP is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And if we're fortunate enough to get a just two, there's a shortcut. But before I go on to that shortcut, let's look at this. RP is the equivalent resistance of the resistors in parallel. RP will always be smaller than the smallest resistance. So I had a 100K, a 50K, and a 25K. You can be assured that the parallel resistance is going to be less than 25K ohms, okay? RP will always be smaller than the smallest resistance in the bank. Now, if you're lucky to have just two resistors, you can use this shortcut. This shortcut here, I think I've presented this in the lectures. Probably did it with capacitors too. R parallel is equal to the product divided by the sum. If you just do this and find a common denominator, you'll find that this is true. Okay, let's see. I think that's, and then we're going to do our series and parallel. We get to the experimental procedure. Let me see if there's anything else I need to talk about. Again, we're going to be doing a virtual, but after this, I'm going to have a few videos where I actually do, and you'll see the reason I do the reason I'm going to do a virtual experiment is because dealing with these little springs that it's just a little kit. This isn't from St. Philip's. This is my own kit that I purchased, gosh, 20, 30 years ago. I don't really recall. I've had it forever. I had to wipe off all the dust for it. I don't think I'd ever used it until we had to go remote. But it's a little hard to use. That's why I'm going to do a virtual experiment using, again, FET from University of Colorado. Okay, and I think that's it for the introduction.